Certifying combinatorial solving using cutting planes with strengthening rules. So the emphasis of this talk is going to be on the second half, namely explaining what cutting planes with strengthening is supposed to mean. But just as by way of background, I think we've all had a great time here in Oberwolfach, but out there in the real world, people are actually not proving exponential time lower bounds for NP-complete problems. They are solving them in linear time with quite some success, using things like Boolean satisfiability solving, constraint programming, mixed into linear programming. And then the really crazy stuff is satisfiability modulo theories, where you also throw in solvers for undecidable theories like integer arithmetic. And they tell us not to worry too much about undecidability because it works beautifully. And it's being done on a daily basis. I mean, the code you're running on your laptop probably has as few bugs as it has because Microsoft has done some fairly serious SMT solving when they were debugging the code. Okay, so there are really amazing progress in this area. And part of why I'm sort of have drifted towards what we refer to, I think, as weak proof systems is that these weak proof systems are sufficient to capture what these algorithms do. And I think it's a very interesting question if we want to understand computation in a real world sense, to understand what systems like cutting planes, polynomial calculus, and resolution, what they really can do, because apparently they can do amazing things. But all is not well. The elephant in the room is that these amazing solvers are buggy, sometimes really buggy. They will return solutions that don't even satisfy constraints, which should be easy, and it gets harder from there. Like if your solver runs for a day on a supercomputing cluster and then reports back unsatisfiable, should you believe it? In general, no. Optimality is another issue, and then people would say, well, doesn't really matter because usually we don't care about optimality. Like in reality, if you're within 5 to 10% of optimal, then that's good enough for the airline company that will take you home. They're still saving millions of dollars. But sometimes it actually does matter a lot, even off by one, and especially if your solver is running inside some other algorithm, then an off by one error can snowball completely out of control. So we do care about errors, and we do care about correctness. So how do people try to address correctness? Well, the obvious thing you can do is software testing, and there are actually fairly advanced methods for software testing these days that work very well, but sort of inherently, all you can do when your testing platform says that it didn't find any further bugs, that means exactly that whatever bugs there might still be, we don't know if they are there. So we want a more principled mathematical approach. And the most principled mathematical approach of all would be to do formal verification. Okay, so this would be basically you specify what would it mean, for instance, to solve Boolean satisfiability. And then you write down a piece of code and you prove a theorem using, Isabelle or Lean or something like that this solver solves this problem. And this would be amazing. And the only problem is that the formal verification methods that exist today are nowhere close to scaling to the highly optimized things that state-of-the-art solvers do. So the one approach that has been successful to address this is what's known as certifying algorithms or proof logging, where your algorithm in general should output not only an answer, but it should output some kind of certificate or proof in a simple machine-readable format that can be verified. So the workflow you get then is, as before, you have an input, you feed it to your algorithm, to your solver, and your solver gives an answer, but it also gives you this proof. And then what you do is you take your problem instance, your input, your answer and your proof, and you feed it to a special checker. And Killian is smiling because you can see the checker box is so much smaller than the solver box. It's a really simple checker because the proof is in some simple format, and we just run the checker. And if it says that everything seems fine, then we really know that this result will work. Okay, so what do we need in order for this to work? Well, firstly, we need a proof system that is very powerful. Apparently, because I mean, when the solver is doing very, very complicated reasoning, we want it to generate this proof with very low overhead. Yes?
I'm surprised that the checker also takes the input. I would expect from the checker, good checker, to tell me that the solver is correct, period, for all inputs.
No, that's the whole point. Before, we're not verifying the solver. We're verifying because we don't know how to do it. That would be formal verification. And we don't know how to do that.
Sorry,
so I'm going to give you something weaker. No, this is a very good point. I'm just going to tell you, whenever you said, I ran the solver on this input, okay, and I got this answer, and the proof is going to tell you that this particular execution is correct. And note that this will, even if the solver is buggy, you might still get a valid proof out of it for this particular execution, and then you can trust that solver execution.
And I presume you are talking about unsatisfiable inputs, because for satisfiable it's not interesting, right?
Unsatisfied in this setting, we should think of unsatisfiability as being the more interesting. Yes, unsatisfiability or optimality or lower bounds on your victim. Yes.
Point.
So okay, so on the one hand, whatever the solver does, we want to be able to write it down in a simple proof. In an expressive proof format without a lot of overhead. I mean, if the solver, for instance, does some counting, clearly it seems like resolution might not be a good idea because we know that resolution will take an exponential overhead to count. So on the one hand, we want a powerful proof system, but we want the checker to be trivial. We want basically a good undergrad ideally should be able to code it up in a day so that we can really, we can just look at this piece of code and say, yes, the checker is clearly correct. Or at least we want to be able to formally verify that piece of code. Now, the undergrad being able to code it up in a day we won't quite get that, but we'll get something close. And there's sort of a clear conflict here between, on the other hand, wanting this amazingly powerful proof system that, on the other hand, is trivial, and you might think that this is a little bit too good to be true. And this is, in fact, what the communities doing combinatorial optimization have been struggling with, because either they have this very, very strong proof system, some of them have, where it's like even verifying correctness is like totally non-obvious what you would do. Or over on the other side, you have very simple proof system that people have been trying to use in SAT solving and in combinatorial, in constraint programming, where you run into the problems that suddenly if your constraint programming solver is too smart, then it will take exponential time to generate proofs. So the reason I'm here and what I've been working on for the last few years is to say that it is actually possible to find a compromise between these two requirements. And what we should do is we should look at the one community that has so far implemented this with the most success, namely our friends over in Boolean satisfiability, sort of the flip side of proof complexity. And they have been using resolution, and then they have been working on different kind of strengthening rules that are sort of extended resolution with a twist. And we're going to shamelessly steal all of their work, except we're going to lift it to cutting planes and then hack it a little bit. And we have done this, we've implemented this in a tool that we call VeriPB, and the amazing thing is that this really seems to work. So somehow our empirical observations, or we zoom out for a little bit, the empirical observation would be that if you're looking at cutting edge combinatorial solving, these solvers that have to run really, really fast, solve problems with millions of variables, it seems that whatever clever tricks they can pull off is something that you can formalize in cutting planes. Okay. And also formalize with very low overhead. So we'll get to that in a minute. So sort of the setting is, jumping ahead a little bit, this is an applied setting. So, saying that two proof systems are polynomially equivalent won't cut it at all. Like we will care about linear factors here.
So just as a question, so you're doing the 0-1 integer linear inequalities, is that?
That's my language.
Yeah, right. So you're focused on that portion of the optimization.
Well, we get to it I'll get to it in a few slides. It's a good question. Yes and no.
Okay.
Okay, so the reason is like, you know, you can translate 0-1 interlinear programs are very expressive. So even if you're solving a graph problem, chances are there is an interlinear program that expresses this problem very nicely. So I'm sort of gonna have parallel processes. The solver is maybe going to run on the graph, but whatever it does, I'm going to be able to describe it on the 0-1 ILP in parallel. Is that making sense?
Sure.
You're sort of pushing me constantly a few slides ahead of myself. So of course I'm here to do a yes.
So what's wrong with the extended resolution?
We'll get to it. It
That's
seems
not
too weak.
Difficult to verify. That's too weak. Oh,
Too weak. It will not do the job. There are certain, I'll get to that as well. You incur, like, at least it seems for some things that we really want to do, we don't know how to get rid of, say, quadratic or cubic overhead. That's going to kill you. Some things, like symmetry breaking, we just don't know how to do. That's going to be one of my open problems. Yeah, so extended resolution is, they've tried it, it has failed. It's a very interesting question whether it would work if we were smart enough. I don't know. Well, I do know that people tried, they failed, we switched to cutting planes, it works. Okay. So, okay, so what do I want to do? Well, I want to, this is a, talk is a marketing pitch, and on a more serious note, maybe this is, I think it's an interesting, for me, it's an unexpected application of sort of upper bounds in proof complexity. Suddenly we have, the reason that we can do this is somehow we have been obsessing trying to prove lower bounds for cutting planes, failing and sort of running into obstacles which were smart things that cutting planes could do. And now somehow we can leverage all of this cleverness of cutting planes to actually certify algorithmic correctness, which is kind of nice. And then I'll try for this audience, I won't show you much or anything really about how we do proof logging, except I'll give you some high-level overview, but I won't really go into like how an algorithm would turn into a cutting planes proof. I'll try to focus on the proof system and highlight some proof complexity clusters for this proof system. So I said it was going to be a marketing pitch. So let's do the marketing pitch right away to get it out of the way. Like, what's the point of proof logging? I think it's important to, the one reason why people started doing this is, well, we want to know that we got the correct answer from our solver. But if you have proof logging, then it turns out that it is a versatile tool that can give you much more. One thing that it gives you that formal verification would not give you is, suppose you run your solver or your algorithm on a supercomputing cluster and it's a hard problem, so it's maybe going to run for a day, you are going to have hardware failures. Some node is going to go down and the master node maybe doesn't notice that it didn't got anything back, or not getting anything back was good news. But in fact, it's because this particular node died or something. It doesn't help you so much that the code was formally verified, because it just, there was a hardware failure.
You can do it twice.
Yes, but even better, I can ask for a certificate. And then I can just offline run through this proof, and I will see, or if there was cosmic rays or whatever, or if my code was correct but the compiler was wrong. At the end of the day, after the execution, I will get a cutting planes proof, and I can just check this cutting planes proof.
So if it is long enough, then you will still you'll need a piece of software to check it.
Absolutely, but sort of, I think you can make a fair argument that if you have a bit flip in the proof at that level, then the probability that it's a bit flip in a bad direction is, like, in some sense exceedingly small.
Okay.
Plus, again, the proof checker is going to be so simple. So yeah, I mean, it's a valid counter argument, but
See some details.
Also, it turns out that the people who do this, the people in combinatorial solving and optimization who we have convinced in doing this, these are people, usually the people that are obsessive about correctness. So they just want to know that their solver is correct, and we give them a tool for proving it. And what happens is, like, every single time, pretty much, you find subtle bugs in the code that they had missed. And that never ever triggered on the thousands of test cases they had, because it's some super weird pathological corner case that the solver is never not checking, but it never makes a difference. But when you run it to the proof checker, it says, like, wait, you're backtracking here. I don't see that you've checked the search space. So it's a debugging tool. And it can also, since typically the proof will be sort of a description of what the solver did, and that means that you can get completely new tools for a very principled analysis of like what the solver did, why did it do it, what was useful for actually solving this problem. You can like look at the proof and you can maybe find dead ends of the proof and trim them and realize that whatever the solver was doing during that part of the execution was not useful, but this led to contradiction. So clearly whatever it was doing here seems to be useful. And then you can sort of do these kind of measurements and look at the proofs and compare to different solver heuristics and see how successful they are. Or you can, once you formalize, like you do proof logging, this has also happened, you realize that sort of your proof system in a natural way suggests additional things that you could do if you're using this reasoning anyway. So why not extend your solver algorithm to try to do something smarter? And then finally, I don't know if you are applying for AI money these days, so maybe, but they're very generous in Sweden at least. So, and things that they care about is, for instance, auditability and explainability. And it's hard to think of anything more explainable than you actually got to prove for like why this solution is the optimal solution and why no other solution is possible. And then even if the solver, I can no longer run the solver, I might still have the proof. And if I know the proof format, I can check the proof of correctness that this instance indeed has this. Okay, so I believe that this is really, these are interesting ways in which we can use proofs. Okay, that ends the sales pitch. So let me now see. So what is our proof going to be? Well, it's going to be cutting place, essentially. So we have 0-1 integer linear constraints, except 0-1 integer linear inequalities. They're called pseudo-Boolean constraints over on the applied side. So I'm probably going to say that. The only thing that but we should keep track of mainly is it's useful to have these inequalities over literals so that I can always pick my coefficients to be non-negative. And this is called normalized form. This is without loss of generality. So just keep it in mind. It will make stating the rules a little bit simpler. And just to make sure we're on the same page, so definitely any CNF formula will in particular be a pseudo-Boolean formula. The nice thing is that you can also express cardinality constraints. Already there, you're gaining exponentially in expressiveness, and in general, we might have any 0-1 integer linear inequalities over literals and negated literals. So this is like what lines in our proof will look like. What are we going and okay? So what can we describe in this language? So we can definitely describe SAT solving, so-called pseudo-Boolean solving. It turns out that we can also do graph problems such as max-clique, subgraph isomorphism, maximum common connected subgraph, and that will be via some kind of ILP translation. Decision problems and optimization problems. What we're working on are things like constraint programming also, automated planning. People who solve these problems, not only do they solve SAT, they can also count the number of satisfying solutions to a formula successfully. So they're solving Sharpie problems as well. So this is something that we hope to publish reasonably soon. And then in a longer perspective, it would be great to also do things like mixed integer linear programming and SMT solving. But then that's sort of getting into, if you want to do mixed integer linear programming, you have to think about like, okay, how am I going to deal with floating point and things like that. So it's a little bit further away.
So for SMT solving, you're thinking of adding another theory on as an adjoint, or?
No, I want this to be like the base language, and the theories should talk to me in this language.
Okay.
And this is very much not what they're currently doing. So they have sort of gone this route of having an extremely expressive, basically their proof language now, as far as I understand, is sort of a union of, like, you will have symbols for every single thing that every single theory can do. And then even like, why is the union of these theories sound is highly non-trivial. So we would, I believe that it would probably be better to sort of try to translate things to some kind of simpler format. Whether that will actually happen and whether that is a good idea or not very much remains to be seen. So SMT is sort of more speculative But the more like Boolean problems and I think integer, as long as you're discrete, I think this will work. Although, I mean, it's there's a lot of work remaining, obviously. Okay, so just to describe a little bit, I'm sort of trying to get to the proof system. I'll get there soon in a few slides, but just to explain how this is going to work. What we're not doing is we're saying, oh, here's a new proof system. We would like you to express your algorithm in this new format and use cutting planes reasoning. That is not going to fly. These people have highly optimized code, and they are not interested in proof reasoning. So you should think of proof logging as you're given the basically some massive piece of code that does whatever it does. And what we need to do is just go through it, understand it, and add judiciously chosen print statements in the code. So that somehow at the end of the day, this will magically be a valid cutting planes proof. This is sort of the piece. So we're really the point is we're not gonna say, oh, you could build another combinatorial solver that does proof logging. No, we're gonna take state-of-the-art solvers and we're gonna equip them with proof generation. Also for this to be interesting, the logging, the actual like how much overhead can you accept when generating the proof? Not much. Say 10% is fine. If it's more than that, then solver authors are not so interested. So that means that again, it has to be very simple to generate these proofs. Checking them might take longer. So like in the SAT competition, they have a factor 9. So say if my solver runs for 1 hour, then I would be okay, or at least I'm willing to accept that it takes 10 hours to check the proof. Yes?
So overhead, in what sense? Length of code or?
Overhead in the sense that if I run my solver, it takes 1 hour.
No.
And if I switch proof logging on, then I'm willing to let it run for 1 hour, 6 minutes. So the extra time generate like solver running with proof logging switched on, solver running without proof logging switched on. That's the overhead.
What is the second time then? Oh,
The second time is the
line, I mean.
Second?
Second line. What's the difference between the first and the second line?
The logging is generating the proof. It's just printing it out.
Yeah.
That should be super fast. Now the solver terminated, and we have this big proof object now.
Yes.
I'd like to know whether it's a correct proof.
Yeah.
So I'm going to go over it and check it.
Yes.
That's the verification phase.
So how much time?
That's going to take maybe a factor 10. So again, if I run my solver for 1 hour, the extra cost of switching on proof generation, 6 minutes. How much time do I allow you to check that the proof was correct? 10 hours.
So let's take it offline.
The surprising thing is that checking takes substantially longer than finding.
No, I still don't understand what 10% is referring to.
10% is the time spent to add the print statements. It's the total cost of the print statement print statements.
So the logging, the proving program, the search program may need to do a little extra work to generate a proof in the right format for the checker. That's about 10% extra. The checker may need to work extra hard, even harder than the logger, the proof generator, to check the proof is correct.
So the checker doesn't get the original proof.
It gets
The checker gets the proof.
Yeah.
Let's take it offline.
Sorry, is there any reason why it takes so long to do checking?
It's a good question.
Just that nobody cares enough to optimize it.
So it doesn't always. Yeah. Okay.
So if you think about it in SAT solving, with watch literals and all this kind of stuff, decisions are being made at an incredibly high rate involving local cache that's very near the processor. These logging statements have to go out and print things to memory, to spot. They're not local.
So it sounds like you could have faster checking, but you'd have to write the proof differently.
There's definitely a trade-off between logging and checking. Yes, definitely so. And there's sort of people would be on the trade-off like really minimizing the logging time. But also it's like the way you generate these proofs, like the way to understand that I think about it, you run, again, suppose you run your SAT solver for an hour, and it starts generating the proof immediately in an online fashion, right? It has no idea whether it's satisfiable or unsatisfiable, or suppose it's an optimization engine even. So you're starting to prove the optimal value of this problem. You have no idea what it is, but you're making some inferences, and you're sort of in an online fashion writing down small comments like I did this, then I found out this, and here was a constraint that seems interesting that is implied. And then at the very last second of this hour, you realize that, oops, the optimal value is 42, and then you have to terminate. And all of these stream of consciousness comments that you wrote down should now constitute a valid mathematical proof. And sort of it's a task of the checker to really, pick up the pieces and say, okay, let's go over this carefully and check line by line whether this is a proof. One problem is that typically maybe 90% of it is not even relevant in the end. But you don't know that, right?
I guess one could also compare the development time spent on checkers to the time spent on solvers.
No, I think it's generally, it's gonna be like the point is, yeah, so if you're a theoretician, you want like maybe polylogarithmic checking time, but that's because you those probabilistic proofs are because you already know the answers, and then you can think about the very nifty encoding of what this known answer is. Here you're building the proof while having no clue what the actual answer is. So the proof will look very different. But you're absolutely right that, it would be wonderful to get it down to like just checking in the same time as solving. Sometimes you can get that. There's definitely work on this.
Just there's also work on compressing the proof once you've got a proof.
Yes.
So
Yes. Yeah. Depending on what you're going to do with the proof, you can also you can try to trim it to sort of find dead ends in the proof tag and just trim them away. Definitely, yes.
So what fraction of the bugs get caught when you add these print statements versus actually verifying the proof?
That is a good, I think it's, it depends in the sense that what we've been doing mostly so far is that existing algorithms and you develop proof logging for them. And then typically what happens is you catch the bugs when your proofs fail to check. Although like all your test cases is passing, but your proof checker is not happy with the proofs. I think for the one area where people are actually now trying to use proof logging during development is constraint programming. And there they claim they've switched to thinking about it really as a very quick sort of debugging tool, because every subroutine will generate like a proof and you can sort of check these proofs locally and see whenever it seems to.
So going back to this question about why checking is so much slower. So from what you were saying now, it seems to suggest that checking is slower largely because there's a whole lot of irrelevant detail in the logged proof, and the checker has to sift it out and find what is relevant.
Yeah,
but I think
not
only. So another reason why the checker is slow is also because in the logging, you want the logging also to be reasonably fast. So you can't really log every reasoning step, and you're on the fly, you're identifying some epochs or milestones and only logging those. And now the checker has to fill in the gaps from milestone to milestone.
That will also be.
Even after identifying which milestone is relevant, there is still work to be done to fill in the detail.
Yes, but it will also be, just the fact that, it will also, but one reason will also be that there is a reason why in our paper we write that, okay, here's a fairly straightforward observation, we leave the tedious proof to the reader. Solvers will also run into this, like, without loss of reality, I can set X to false now, and I will not lose out on any optimal solutions. It's like, yeah, but in order to verify this, I have to carefully go over the whole database and check.
Right.
And this actually happens. Okay, so how do we do the proof logging then? Well, if you're solving SAT or if you're solving 0-1 interlinear programming, then you're all set. The language is the right one. But otherwise, so then you just add print statements to the code. Otherwise, what we do is we somehow have to find a 0-1 interlinear programming representation of the problem you're interested in. And then we are going to do the proof generation in this formalism. It's very important, so this is a common misconception. We don't translate the solver to an interlinear programming solver. The solver will do its thing with its own representation, But somehow I'm going to argue that every reasoning step can be formalized in terms of this integer linear proof. And as I think I've already said now, somehow it just seems empirically that cutting planes is, well, it's an expressive enough formalism, but it's, although simple, and it's also a lot of what combinatorial solving is about. For instance, graph solving algorithms, how do they actually solve clique or subgraph isomorphism? Well, they basically explore graph neighborhoods and count graph statistics. Cutting planes can count. Also, a lot of the very sophisticated, like, okay, constraint programming, they have constraints that is like the Hamiltonian circuit constraint. So you have one constraint that is, this graph has a Hamiltonian circuit, and if it doesn't, then please backtrack atomically in one step. Okay. So this is just running this propagator and seeing whether it propagates or not is like a highly non-trivial algorithm. But it turns out that the kind of algorithms they use to detect whether we now have a Hamiltonian circuit or not is formalizable in cutting planes. And again, this is an empirical observation more than anything else. Yes?
So basically, you need the logger system to be strong because you need to simulate. Do you need to be able to simulate?
Kind of, yeah.
Every step of the solver?
Yes.
Okay.
Yeah. Okay, so the actual workflow, and maybe this sort of connects a little bit to why we need the input also, because now you realize that, well, who checked this 0-1 ILP translation? Well, in the first phase, this is not what people are worried about. Like, you know, we can write down a 0-1 ILP capturing clique and we will know that it's correct. So like, if I give you a proof logging for this 0-1 ILP encoding, you will already be very happy. But of course, the gold standard will be to use formal verification for the checker. So like the full workflow is that you get your input, and then the solver sort of says that, okay, here's the 0-1 ILP I'm going to think about. This is the translation of the input, and the proof is going to be generated for this. And then at the end, you're going to take all of this, you're going to take the original input in the graph format, you're going to take the 0-1 ILP proof, and you're going to feed it to a formally verified proof checker that checks A, this 0-1 ILP translation of the problem is okay, and B, given this translation, I agree that you have proved the correct optimal solution for this 0-1 ILP. So this is like the full framework. Okay, finally, so what is our proof system now? So it's important, it's going to be a configurational proof system. So I will carry around with me like all the constraints, all the 0-1 integer linear inequalities that I know. Importantly, there is no such thing as if you've done like space complexity in proof complexity, we usually have like the formula on an input tape. We don't have this here. So we start with the formula and we have it in memory. And if you're going to erase anything from the formula, then it's gone. And like in general, that's not a good idea. So we're not going to do that in this talk. And so you can think of there will be a core set of constraints that is the formula. And at all points in time, in some vaguely formulated sense, we'll make sure that this core set is equivalent to the formula. But for instance, it stands to reason that if I identify that some variable unconditionally has to be true, that might allow me to simplify some constraints, and I should be able to do that and sort of keep the simplified formula in the core set. Everything I derive will end up in a derived set. And what will that be? Well, typically anything that the solver actually derived, like if you have a SAT solver, it will derive new clauses, they will be over here. Another thing that will be over here is maybe some extra constraints that the solver has no clue about, but that I'm doing as part of my proof logging process just to help justify correctness.
Can you delete things from the derived part?
From the derived set, yes, we'll get there, but deletion is completely free. So that's the whole point. Like this will sort of be equivalent to the formula. How this grows or shrinks is more a matter of convenience. Yes. Then I won't dwell on it too much because I think we're interested in decision problems, but there will be an objective, which is a 0-1 integer linear function to minimize, or a fine function, I guess, if we want to be precise. And sort of the proof will know what the currently best lower bound is, because there are rules to force solutions for better bounds. I will mostly ignore this, except that it will make one reappearance later in the talk, maybe, if we get there, where even if I don't have an objective, it can sometimes be helpful for me to just invent an objective. And I hope you agree with me, if all that I'm interested in is the decision problem of satisfiability, if I find the satisfying assignment that optimize my favorite objective, that's sort of the same thing as solving satisfiability. Okay? In particular, that's super useful if you do symmetry breaking. And I will mostly completely ignore the fact that we can sort of also reason with respect to orders, which is any order relation, and you can actually plug in your own order relation as long as you provide sort of in a preamble of the proof, a cutting planes proof that this order relation is an order relation.
Sure.
Mostly like the second half of this slide, we can mostly ignore it. This is just for completeness. If we keep track of the core set and the derived set, then we're good. Okay. And the axioms are as from the input. Then we have that all variables are between 0 and 1. Conveniently, all literals are non-negative. And then we can do addition, multiplication. The division rule looks like this. For any 0-1 integral linear inequality with non-negative coefficients, I can just divide by C everywhere and round up everywhere. Okay, and if you're worried about this, this is sort of equivalent to the standard rule where we would have a common factor C on the left. Another interesting rule is the saturation rule, which again says in normalized form, if I have a large coefficient here, no coefficient here needs to be larger than the so-called degree of falsity, the constant. So the saturation rule just says that basically trim all these coefficients down to at most A. Okay. And just to make sure we're on the same page, so what will we do? So, you know, in the cutting planes derivation, this is sort of what will happen in the proof. We will have some kind of constraints. One of them will multiply by 2. Then apparently we have some other input constraint. We can add them up. Then we have a literal axiom. We can multiply it by 2. We can add up. And now we have a cancellation on Z. And we implicitly simplify. And now we can divide. And just to keep things simple, we actually do divide evenly the left-hand side and round up. Okay. And the way this will look in the proof system is that every constraint that I've seen previously has a number, except axioms that look like tilde is negation. So if this was sort of, if I know that this is constraint 1 in my database and this is constraint 2, then this kind of tree-like, every proof line will sort of be a tree-like cutting planes derivation that will look like this. So this is actually what our proofs will look like, lines like this. Yes?
Can saturation simulate division or not?
Excellent question. Yeah, this is so why are we even using saturation? Well, firstly, it turns out to be convenient. Secondly, when people started implementing what they call cutting planes based solvers, they're actually not using division, they're using saturation. I am not sure why. I think they themselves are not sure why. And for me, you know, as a complexity theorist, you immediately want to know how do these rules compare.
No, actually, I have an even simpler question. If you remove division, will it remain complete or not?
No. Okay, so cutting planes with saturation is not implicationally complete. It's refutationally complete. It is not implicationally complete.
But then it answers your question in one direction.
It does, yes, right. So we know actually and we also know in the other direction, I can give you explicit constraints where I can tell you like, here is something that saturation can do. Division can obviously simulate it because it's implicationally complete, but it will take you an unbounded number of steps.
No. But it does direction, the answer is simply negative because you cannot simulate complete proof system with incomplete.
But what we don't know and what would be interesting, so on the one hand, the two rules are clearly incomparable. Okay. But then you can say, what about cutting planes with saturation and cutting planes with division?
Yes.
Then we know that cutting planes with division can be exponentially stronger for the stupid reason that I give you the pigeonhole principle formula in CNF, and cutting planes with saturation will not be able to rewrite it to a 0-1 ILP.
It's in.
But we do, in the other direction, we don't know.
Yeah, that
We
makes
don't
sense.
know whether cutting planes with saturation, whether there are, it would have to be 0-1 interlinear programs and not CNFs. We don't know if there are 0-1 interlinear programs where cutting planes with saturation would be more efficient than cutting planes with division. I don't.
Very interesting. Very good question.
So actually don't know the rules to be incomparable, or in what sense they are incomparable with?
They're incomparable in the sense that cutting planes with division is always implicationally complete. And it's not hard to see. Okay, so for instance,
Okay.
cutting planes with, if I give you, x plus y greater equal 1, x plus z greater equal 1, y plus z greater equal 1, and I give you cutting planes, linear combinations, multiplication, and saturation. It's an exercise to prove that I cannot, never ever, in no length, derive that 2 out of these 3 variables are true. Cutting planes with saturation is just not able to get this. This is a nice exercise. Okay, so in that sense, clearly, like cutting planes with saturation is like weaker. It cannot even derive this. Okay. In the other direction, I could also give you similar inequalities where saturation just gives you a nice consequence in a single step, but where the number of division applications you would need would be an unbounded number and would scale linearly with the magnitude of the coefficients in the expression in question. And that is the reference, that's the reference, and all references will be at the end of the slides, and the slides are already online on my web.
Just to make it totally clear, this shows separation for implicational completeness.
Yes.
Do we have separation just in terms of refutation size?
Yes, as I said, so now if I give you the pigeonhole principle in CNF, it's not so hard to show that cutting planes with saturation, for any CNF, cutting planes with saturation will be a resolution. Okay, so now you have your separation.
Oh, will be resolution means.
Yeah.
Yeah.
So cutting planes with saturation, if I give it a bad encoding, CNF encoding, then it will be glorified resolution. Okay, here comes the redundance rule that is important for some rule applications. So we say that a constraint C is redundant with respect to a formula F. If, well, F and F union C are equisatisfiable, and as I think this condition is essentially from Sam and Neil, that this holds if and only if I can come up with a witness, this is a substitution mapping variables to truth values or literals, such that F union not C implies F and C under the substitution logic. Like if this holds, then you should agree that adding C does not change the satisfiability status of F. Let me sketch a proof. The interesting direction is that I have a truth value assignment that satisfies F but violates C. That's what I'm worried about. But if so, such an alpha satisfies the left-hand side, so alpha must satisfy this. And if you just unpack what this means, that means that alpha composed with omega satisfies everything. So this witness is like a local patch that tells you that if you get a satisfying assignment that is no longer valid, how do I patch it? So our proof system will allow to write derivations in this way. And importantly, in the implication should be efficiently verifiable. So I will have to give you, write down in the proof exactly what omega I have in mind, like list the domain and what the values in the domain map to, the variables in the domain. And then I have to be able to verify for every constraint in here that it actually follows from here. And in the actual version of the proof system that we use, we allow you to give derivations. Why not? Okay, but even the version where you just say, okay, every constraint in here should be, say, a weakening of some constraint in here, that is essentially, I think, for practical purposes, pretty close already. Okay.
Why do you confine yourselves to substitutions of this particular kind? You can substitute whatever you like.
I want to stay within, these should be like also 0-1 interlinear inequality.
You want to preserve
Yes.
pseudo-Boolean.
Okay, so let me see, we're actually not doing so well on time, so let me maybe skip this. This is just to say, okay, suppose I want to have a new variable a that is equivalent to x and y, then I can just in pseudo-Boolean form, this is deriving these two inequalities, and I just do it by two applications of the redundance rule. And the point is that sort of the witness is exactly our reason for sort of understanding that this is okay. Like, okay, you're saying here, well, what if x and y are both, what if one of them are false? Well, then it's okay because a will also take the value false. And this is sort of what this witness says, that you know that this is okay because you could always set a to false. You know that this is okay because you could always set a to true. So sort of the actual mechanics of the rule match pretty closely our intuitive understanding. And now, of course, you realize that we already have extended Frege. So proving lower bounds for this proof system is going to be hard. But there are two interesting cases that is not clear to me whether they're hard or not. Note that the way this rule is formulated, we don't need new variables for it to make sense. Like this rule makes perfect sense even if you cannot introduce new variables. Okay. So what is the strength of the redundance rule if I have to stay within the variable domain of the formula? What we do know is, for instance, the pigeonhole principle and old Sating formulas are easy. So resolution with redundance can do them. Can we somehow develop techniques to prove lower bounds? Slightly more ambitiously, what if I allow new variables, but they can only be equivalent to clauses that I already know to be true? How useful is that? Why do I care about this? Well, it corresponds to the only example of successful extended resolution reasoning I know, namely what is done in so-called core-guided MaxSAT solvers. And they essentially do this, sweeping a lot of stuff under them. Okay. And if we want to formulate this rule in the very PB system, we have to say that we have this core set, we have this derived set, and this together with not C should imply everything with C added under this witness omega. And then if I have an objective, it's very important that when I patch my assignment, I should not make the objective worse. So I'm always minimizing my objective. Okay. So, but interestingly, once I've phrased the rule this way, suppose that I have an objective and the witness omega strictly improves it. Then I can actually be more aggressive and I can allow a dominance-based rule, which says that if I can find a witness such that the core set union the derived set union the negation of what I want to derive, it's sufficient to prove that this implies the core set under omega and that it decreases the objective strictly. Then it's sound, or at least it does not change satisfiability, or it doesn't worsen the objective value to add the constraint C.
So what's the point of this second rule again?
Well, the point is now that I'm making my life much easier. Here I just need to prove that these are implied, whereas before I needed to prove all of these guys.
Okay, but
Okay. And that's a big deal, it turns out. So let me try to sketch very quickly why this rule would even be sound. Let's suppose that the derived set is empty for simplicity. Well, I have an alpha that satisfies C, the core set, and let's say that D is empty. If it would satisfy the new constraint C, then we would be happy. So suppose it falsifies C. Well, then again, we know that the left-hand side is satisfied. So the right-hand side is satisfied. And composing alpha with omega gives me an alpha with a strictly smaller objective. That is guaranteed to satisfy the core set. If it satisfies our new constraint, we're done. Otherwise, the left-hand side is satisfied again. So we compose with alpha. And we get a smaller value of our objective. And the core set is satisfied. So if the new constraint is satisfied, now we're done. Else we repeat again. And we're over the Boolean hypercube and we're getting strictly smaller values, integer values all the time. So this is going to terminate, right? So this is sort of the way I view this. This is cutting planes with some kind of poor man's induction. Okay, and there are, again, we're running a little bit out of time, but there are other sort of extensions you can do to this. And okay, we already had extended figure. What happens when we add the dominance rule? Do we get even more? And Neil will tell us that maybe yes, after the break. We talked briefly about deletion. You cannot, so deletion now turns dangerous with these rules. It's sort of obvious that if I delete too much, then I would have an unsatisfiable formula and would turn satisfiable. Not so obvious, I could also have a satisfiable formula and make it unsatisfiable if I don't restrict deletion. So I have to be a little bit careful. And this is why I have a core set and a derived set. You can always delete from the derived set. From the core set, I can only delete a constraint if it can be rederived from what I have in the core after I've removed C. And that then you have to argue why this maintains soundness. And this is actually something that the SAT people already had when they designed their DRAT proof logging system, but they never implemented it. In order for this to make sense, I want to be able to move things from the derived set to the core set. For instance, if I simplified, if I knew that a variable is true, I will typically add it to the core. If I want to change, okay, we didn't talk so much about orders, but you can sort of change the order with respect to which you're doing your derivations, but then the derived set has to be empty because otherwise, again, ugly things can happen. Okay, with this proof system, you can do EXO reasoning efficiently for the first time. So before, people with SAT solvers that did Gaussian elimination had to switch it off in the competition. Now you can do it with our tool. I am sort of running out of time, so I'm just flashing the slides. Even more importantly, for the first time, if you want to break symmetries, what we will do is, even if you're solving satisfiability, we'll pretend that we're optimizing this objective. We're minimizing this objective, and what this will do is it will find for you the lexicographically smallest solution. And then it's completely trivial. You just derive that you want. This is sort of the Lex leader constraint saying that I will only allow a solution if substituting the symmetry omega will not make the objective value smaller. And this is like one simple application of the dominance rule. It's immediate. You don't even have to write down anything. And then once you have this, you can easily derive the standard CNF encoding that will break symmetries in a Lex leader fashion. And this actually works. It's efficient. We had it in the SAT competition last year. Okay, we're trying to get towards the end. Let's see. But one thing that I don't know is, do we really need the dominance rule to break symmetries? Because there are some, like pigeonhole style symmetries can be broken already with the redundance rule, in fact, even with the DRAT rule. And I think it's like generally open whether we could be smart enough and just use redundance to break symmetries completely. Is that possible, or do we really need dominance? One other thing that is really annoying that I don't know how to do, and I'm trying to wrap up in just a couple of slides. One thing that also shows up in applications is if you already done some type of reasoning, for instance, when you're doing graph solving, and you know that for any neighborhood like this, I know that there is no subgraph isomorphism in here. And if I know now that another neighborhood of the graph looks exactly the same way, I would like to argue that it looks the same way. I already know that I couldn't map into there, so clearly I couldn't map into here. You would basically need substitution proofs for that, or you would need to derive a lemma that you can apply again. I don't know how to do that. I would be very interested in finding an efficient way within this proof system to do this. There is a reason why it might not be trivial. If you think about it, like extended Frege is sound, substitution Frege is sound. Now, if I take a Frege system with both extension and substitution, that's not going to be sound. And this is sort of the problem we're running into. I know of some ways of doing it. They're extremely finicky. And be happy to talk about that. Performance, we'd be happy to improve that. Also, trimming the proof to get rid of details that you don't need. In practice, getting a binary proof format would be nice. I already talked about other applications such as mixed integer linear programming, SNT solving, model counting. I think there are lots of, once we have these things in place, there are lots of interesting questions about algorithm analysis where people with a proof complexity mindset could make lots of interesting contributions. So I always flash this, that we're on a crusade. If you want to join the pseudo-Boolean proof logging revolution, then we're hiring. If you're a, PhD student or postdoc. Okay, so that, and there's lots of documentation available, a fair number of papers by now that is implementing, showing how all kinds of different types of combinatorial reasoning can be implemented within this cutting planes with strengthening rules system. Combinatorial solving, the solvers are amazing, coming up, but ensuring correctness has remained an open problem. As of today, this idea of equipping solvers with proof logging seems to be the best approach, the most promising approach. Cutting planes seems to be the proof system made for this, which is an accidental discovery, but it really seems to work. What I've tried to convince you about, although I had to go fast, is I tried to highlight some questions where I think there are interesting proof complexity questions that we could study. Okay, so that's it.
Can you go back to, you had the XOR reasoning that you skipped over?
Yes.
That'd be just nice to see how that works.
Yeah, so, okay. So basically, so firstly, if I have these clauses, I should be able to derive XOR not W and not XOR W. Why? Well, because this is just saying that X XOR Y XOR Z is odd, and this is saying that Y XOR Z XOR W is odd. So I just add them up and I get that X XOR W is even. Of course, resolution can't see this, but a SAT solver with Gaussian elimination would detect this. How would I build a proof for this? Well, first I will derive that I don't know what X plus Y plus Z is, but without loss of generality, there is a variable A such that X plus Y plus Z plus 2A is equal to 3. This I can derive in cutting planes with redundance. And now you look at this, you realize that this is XOR, right? Because A is going to give an even contribution. And in a similar way, I'm going to derive that Y plus Z plus W plus B equals 3. A and B are fetch variables. And now to simulate Gaussian elimination, for instance, this is obviously a toy example, but just add them up. And now I see that everything has an even coefficient except X and W. So clearly X plus W has to be even. So I've actually derived that the XOR of X and W is even. And the only question is, yes, but it's sort of hidden. Can I extract it efficiently? The answer is yes. I think it's this example, in fact, we've worked out, like completely showed how to do it. And again, this is sort of, this works in practice. Obviously, what you would do, you'd run your Gaussian elimination solver, but whenever it makes a Gaussian elimination step, you know which equalities and inequalities you want to add. So this is again like the Gaussian elimination engine is completely unaware of this, of course, but I'm just building a cutting planes proof that sort of mirrors what the Gaussian elimination is.
Do you need large coefficients?
Yes, sometimes large coefficients will be very important. Yes, typically, yeah. Yeah, this will be, in particular for symmetry breaking, we need exponentially large coefficients. Yeah, which is not but the bit size is scaling nicely with the instance size. So the exponential coefficients we use, there would be a way of breaking symmetries in constant size coefficients. We never had the energy to implement it because exponential size coefficients works just fine.
Yeah, in curiosity, so you said in the actual workflow, like after you have your checker, you have your checker make clean up the proof and give it to a formally verified checker.
Correct.
And I'm curious. Is that like catches / caught bugs in your checker?
It does. Definitely, yes. The formally verified checker is a great way of debugging our proof checker, yes.
So
One last question.
Which is like one reason why I think you really want formally verified proof checking. Because in the end, as you can see, that the proof system wasn't quite as simple as I want.
So you had very PB you talked about all the time, and then you mentioned Cake DB on the last.
Yeah, so Cake PB
PB.
is the formally verified backend in the Cake ML environment that is using I think it's using Hull to sort of it's an environment where you can go from mathematical definition all the way to provably correct machine code. So developed by Yongkiam Tan in Singapore, Magnus Muren at Chalmers in Sweden. So you have like basically what you start with, you start by actually defining our proof system mathematically. And then you actually write down theorems saying why the dominance rule and the redundance rule are sound, for instance. And then there's like layer by layer, you sort of prove that more and more fine-grained implementations of checking algorithms. And then the very last step, you get like machine code that will take a proof that very PB has cleaned up and simplified a bit and removed, because all of these things where I don't have the energy to write down the details, the proof checker, you'll have to figure it out. Like Cake PB will not be willing to do that in a formally verified way. So very PB will elaborate the proofs, ship them to Cake PB, and Cake PB is fully formally verified and basically is able to just add up, divide, zero and interlinear inequalities. It's also able to do things like plug in substitutions and check the things that are needed to check redundancy.
Okay, I think further questions can be asked in the post. Thanks, Stephen. We'll get back at 10:30.